So this was a really good worksheet. I mean, it doesn't really ask you to do too much with what we were supposed to have gotten through last class, which we didn't all the way get through. But it's mostly a review over just our general probability rules and some other stuff. So starting with A, what is the probability a randomly selected rat will weigh more than 940 pounds? Or grams. I was like, dude, that's a huge rat. Grams is a lot different than pounds. Once you get one more time. 0.136, 0.1357, 13.57%. All of those make me happy with their answers. Good. This was just a normal CDF problem. And for these problems, please remember, it's been a long time since we've done this. Okay? It's been a long time. Shouldn't have left you without a dope beat. Step two. No?
That's going to be
Yeah, I just realized that. So what you need to make sure that you're doing with this is you're saying, okay, X is, for example, the distribution of rat weights. Just a fun topic. In grams. Is that how you label grams? I don't know. Whatever. Just G. I don't know. Just G. Okay, and you would say X follows a normal model with a mean of 775 and a standard deviation of 150. And then you would need to calculate the z-score, which is what this is doing right here. So it's saying my observed, 940, minus expected, over standard deviation. You have to show that. It's been a long time since we've done just these basic problems.
If we put 940 in normal CDF, you get the same thing.
If you're putting it in with these adjusted things. But whenever you calculate that, I totally agree that you get the same thing. But whenever you're doing this on the AP test, they're always looking for the test statistic. And the test statistic is that 1.1. Whether you use the 1.1 in your calculator when you calculate the probability or not, I don't care. You are more than welcome to say the probability that X is greater than 940, or what they have, Z is greater than 1.1. Either of those are perfectly acceptable, but you have to talk about context, describe, statistic, what are you finding? Okay? And if you've got all of this, especially these top two things, the rat weight, the X goes from whatever, follows the normal distribution. For the next problem, all you would really need to do is what it's asking, which is to draw and label the curve. So you just put 700 and 900 where they fall respectively to the center, to the 775. And then you can just tell me what the answer is, again, in context. So what we would say is we would expect 48.9% or 0.489 of the lab rats to weigh between 700 and 900 grams.
How did you find that?
This guy?
Yeah.
Normal CDF from 700 to 900, lower, upper, with a mean of 775 and a standard deviation of 150. Okay? Since you're drawing your picture, that's good enough, and they're not going to expect to see the standard deviation on it, or the z-score on that one. Now for problem C, it's saying what are the chances exactly 4 of them weigh less than 940? We're going to be doing that later on today. Okay? That's not stuff that we didn't get to last class. It's just stuff that we're doing later on today. All right, talking about number 2. What you need to start with, again, this is all about what kind of work do you need to show. Because this is where people lose those points, and you don't want to be one of those folks. So they're saying if a house has 3 bedrooms, what is the mean and standard deviation? Well, the first thing that I want to do is I want to define, I'm just going to say X is a bedroom, and then I'm going to say Y is the kitchen. Okay? All right, so it says a house has 3 bedrooms. What is the mean and standard deviation of the total area of the 3 bedrooms? Now, is that 3 X's or X plus X plus X? X plus X plus X. So this is the expected value of all 3 bedrooms added together. And the reason why we do x plus x plus x rather than 3x is we're not saying every single bedroom has to be the exact same size. I mean, most cases they're not. Right? We're all right with that? Okay? So when we calculate the expected value on that, mine is wrong because I grabbed the wrong number. It should be 3 times 200. The expected value should have been 600 square feet. My standard deviation, however, is correct. 112.58 square feet or feet squared. Are you okay with that? Again, I know mine's wrong for expected value. I apparently can't read problems. Yes, sir.
So you want us to show the defined variable and show the...
Yes. Yes. Yes, ma'am.
For mine, like the way I wrote mine. Oh, that's for the next one.
Okay. Now, the next one is really kind of, I think it's a tricky question because it depends upon what you try to do to set it up. And for the next problem, what they're saying is that the house has lunch. Go to lunch. We'll finish this when we get back. Okay, so we had gotten up through talking about part A. Part B, like I said, I think this is really the most tricky aspect because this doesn't work for traditional algebraic equation. You can't just move variables around however you want. You have to think which ones are independent and which ones are dependent. So if I'm talking about a whole house and the rooms that make up the house, whose square footage do I set? Do I set the square footage of the entire house, or does that come from the square footage of each individual room? So it's like I say, I want a 2,000 square foot house. By golly, everything's going to fit in that.
Don't you like
No.
the house first and then?
Well, you do, but like when you're making the layout, you kind of say, I want my bedroom to be about this big, and I want the living room to be about this big, and let's kind of stretch this, and we'll do that. And how big the house ends up being is just how big the house ends up being. Do you understand what I'm talking about? You can change the size of the individual rooms, which will in turn affect the overall size of the house. But you normally don't get to say, I want a house that has 1,800 square feet exactly. And then kind of like, how am I going to make that happen with the rooms that I need? It doesn't work that way. So when we're talking about our equation for this, we get to say the whole house is made up of 3 bedrooms. So x1 plus x2 plus x3. And a kitchen. So there's my y. And something else. All the rest of it. Okay? That's going to be the equation for my house. So when I'm talking about the average and standard deviation for the living area after the bedrooms and kitchens are excluded, we can say for the expected value of the house is 2,000. And that's going to be equal to the expected value of the 3 bedrooms, which was 600, plus the expected value of the kitchen. What was that? Have an average of 300, plus everything else. So I can easily figure out what the expected value of everything else is going to be just by doing basic addition subtraction, because expected value is easy. And that rest of that stuff should have an expected value of 1,100. Oh, your closets, your living room, your bathrooms, your all that other stuff. Okay? What gets a little bit trickier is when I want to talk about the variance. I cannot just solve this equation, house equals bedroom, 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 kitchen, stuff. I can't just solve it for stuff and then calculate the variance. Because it's like talking about a triangle. A, B, and C. I cannot give you A and C and just say, oh, okay, so B squared is, or B is just A minus C. I can't do that. So what we have to do here is we're going to say the standard deviation squared of the house, which is 225, is equal to the standard deviation of each of the bedrooms squared. So that ended up being, what, 65? 65 squared plus 65 squared plus 65 squared, plus the standard deviation of the kitchens, which is 45, so plus 45 squared, plus that other stuff squared. So you would take 225 squared minus all of the rest of it, and then take the square root. So the standard deviation of the rest of that stuff ends up being about 200.81 feet squared. Yes, ma'am?
Why would you take the square root of it
Did I?
Yeah, you said.
Okay, so yeah, I see, because I put 45 here, that was supposed to be 65, this was supposed to be 45, so let's see what it actually works out to be. So I'm going to say 225 squared minus 3 times 65 squared. Well, when I go and I solve this, I'm not subtracting the variance. You see, all of these guys are added together. So what I'm going to do is I'm just now going to solve that equation. So I square both sides, okay? And then I'm going to subtract the stuff that I have and leave with what's left. So here, I'll go ahead and write it down. Give it a second to pull up. Okay. Flip, zoom, focus, and project. Go. Okay. Let's do this one more time because that's way too dark. All right, where we said the expected value of a bedroom was, what was the bedroom? What was it? For the size?
Just
Bedrooms. Bedrooms expected was 200. Standard deviation of the bedrooms was 65. Expected value for the kitchen was 300. Expected value, standard deviation for the kitchen was, one more time, 45. And then I'm just going to use house. So expected value of the house is 2,000. Standard deviation of the house, 225. Thank you. And we're saying the house is made up of the 3 bedrooms, kitchen, and whatever else is there. We were able to do the expected value for that pretty easy. There's no tricks with expected value. You just kind of figure it out. But when we're talking about the standard deviation or the variance, the way that equation works out is we're going to say the house squared is each of the bedrooms squared, the kitchen squared, and then whatever the other stuff is squared. So if you look at this, I really am not, although I might use subtraction to solve for it, my variances are only adding. So now I need to solve the problem. So I can just do 65 squared times 3. So that's the 3 bedrooms. The kitchen. Nope, not the other stuff. So far over here, I have 14,700, whatever the other guy is. Where's the squared button? There we go. 50,625. Helps if I write the numbers right. And so I'm just going to subtract from that the 14,700. Okay. So then I have 35925 is the standard deviation of everything else squared. So I'm going to take the square root of that. And I get 189.539 square feet. Okay? Does that make a little bit more sense? Now that's a really tricky question, but that's the type of problem that if they were to do an AP question that they would ask you. Understanding the fact that you have to consider what are your dependent and independent variables. And like, for example, I really want to build a new house. I really do. I'm not kidding. I'm like looking for land and everything, and I've got my floor plan picked out. And I can't find a house that has, I want 2,000 square feet. It's a nice number. I like it. But I also want a certain number of rooms, and I want the rooms to be a certain size. So I can't just like fit that. I have to kind of play with the rooms, and however each room figures out, the total house's area will kind of play around with that. Yeah, I haven't been able to hit 2,000 exactly yet. I'm not going to. I realize I'm not that's just crazy. But for these problems, when you're setting up this equation here, you are not able to solve first for z in this equation and then do variance, because that will affect what your answer is. Okay? All right, number 3, we are moving on and we're talking about some more of our probability. So A is saying randomly selected individual listened to a CD, and yes, this was wrong on your paper. It said 200 total. There was 260. What is the probability that a randomly selected individual listens to a CD? 0.46. 0.46 something or another. Because what you're looking at this is you're talking about anybody who listened to a CD. So that means both of these groups, 56 plus 64, divided by the total of 260. Okay? Now, when we're looking at B, it says what's the probability someone listened to music on a CD that also listened to digital music? Is this an and, an or a given problem? This is a given problem. So don't really say the word and. They say what is given. They listened to music on a CD. Someone listened, that if someone listened, whatever follows the if, that is your given. Okay? So for this one, we're only talking about, we've got CD people, so I'm looking at that 56 and 64, and we're talking about the digital music. So 56 out of 120. So 0.4667. And again, I really need to see those fractions for this. They won't give you full credit if you don't show where your fractions come from. Yes, ma'am? If you just put the fraction, you're good. You don't need the decimals, but you do need the fraction.
No, I mean do we need the probability of digital and?
No. The explanation aspect of it. No, you don't. It can help you. Again, if you had this set up correct, but for some reason you grabbed the wrong number, that can always benefit you. Okay? And so when we're talking about, are these independent, what would you say? But look, 46.2 and 46.7, those are really, really close. It's not that they're not the same. Can I even compare these two numbers? No. Because when I'm talking about given statements and I'm talking about independence, you've got to be very, very careful. So for this problem, I have to show the probability of a CD, and you compare it to anything else as long as the CD comes first. Given digital, or the probability of a CD given no digital. Okay? You have to make sure that first piece matches. So it's not the problem that these two numbers, 46.2 and 46.7, are different. Because remember, we said as long as you're within like 2%, okay. But it's because those aren't even the right things to compare. If I've got digital given CD, then the other thing I should compare is just digital. So you could have done any of these comparisons. Digital given CD versus digital, or digital given no CD. You could have compared digital CD, digital no CD, probability of CD given digital, CD given not digital, digital. I can't even speak anymore. Digital. Yes, Allie. In the way this B was phrased.
Yeah.
C is completely different.
Oh, digital given CD.
It's okay. So you figured out where, okay. Yeah, it's always the given. I know that sounds weird. You want to say, hey, that first guy happened first. But what we're interested in is the probability of digital given the CD occurred. Okay? You clear on that? All right. Just one more problem. Any other questions on this one? Okay. So now we're back to our regular probability. So what is the probability you win 20 bucks 3 times in a row? 0.002. I was kind of hoping that would be quite simple. For your guys' quiz, there were a few people who were struggling on a problem like Part B, and the biggest issue was you didn't properly build your model. Here's my question for the models. What do all of your probabilities have to add up to? 1. There were a lot of people that didn't have that. Because they said, oh, okay, I could win 20 bucks, I could win whatever. So this one is saying if we played the game 20 times, how much money would you expect to win or lose? Well, for that one, you set up your overall goal, playing the game 10 times. So, this is showing you the expected value of just one game. So what we have here is 0 times 0.5 means you break even. 15 times 0.125, that means you won the $20 minus the 5 that you spent. And the negative 5 means you just lost. Okay? And then because we're talking about 10 separate times, 10 doing 0 plus 0 plus 0 plus 0 10 times is still 0. Okay? Now, what do you think for C? It's your favorite question ever. Law of averages doesn't exist. Don't tell me, no, law of averages. There's no such thing as the law of averages. So just telling me the answer is no because of the law of averages is like completely wrong. Okay? It's that idea that these guys should be independent. It doesn't matter what's happened before. Yes, ma'am?
I still don't understand how I got it.
Okay. So when we're talking about one of those problems, there it is. So we have a game, no matter what, it costs $5 to play. Okay? If you roll an even number, you get your money back. So if I get your money back, how much do you walk away winning? 0. Okay? It says if you roll a 7, you win $20. He gives you back $20. So how much do you walk away with? You now have $15 additional dollars. If it's neither one of those, you walk away -5. Sorry. So what we do is we build our probability model here. This is the event. This is the probability of the event. So I win no money if it's even. What's the probability of being even? It's an 8-sided die. 4 out of 8. Or 0.5. If it is a 7, I win 20 bucks. So that means I come back with $15. So how many of them are 7s? 1 out of 8. And that leaves me to walk away in the red with less money than I started with. How many 8s are left? 3. So to find my expected value, you can either type that into your calculator or say 0 times 4 8ths plus 15 times 1 8 minus 5 times 3 8ths. That walks away with 0. That's not 10 games. This is 1 game. But if the expected value for 1 game is 0, and we're playing 10 of them, 10 times 0 is 0. Okay? Does that make more sense?
So you just add all the possibilities probabilities in one game that can happen.
Yeah. Hannah, wake up. Okay? And then we talked about C. So what we're going to do now is we are going to pause with this, and we are going to go back where we left off from the last class. I think this is it. Nope, that's not it. This guy here. Here we go. So this is where we were the end of class. We just kind of took a little more time than was expected. That's okay. Today what we'll do is we're going to finish up the geometric model, do some practice problems. We'll talk about the other model, and whatever we don't finish today, we'll get to next class. And so that just means that your quiz is going to be on, okay, today is Wednesday. Your quiz is going to be on Tuesday of next week. Your test will be on Thursday of next week. Okay? Or wait, no, today is Wednesday, so your quiz is going to be, no, I was right. That's the other class that I'm doing weird stuff on. So quiz is Tuesday, test Thursday. All right. So what we were talking about last class was the idea of a geometric model. And in order to be a geometric model, what did I need to have? What were my assumptions and conditions? Independence. One event could not affect the other because that led to the idea that your probability of success had to be consistent. Right? There was one more thing I needed. One more time? Binary. Success or failure. And that doesn't mean success is the good aspect and failure is the bad. It's just success meets the condition I'm looking for, failure doesn't. And then in order for it to be a geometric model, and you're really going to need to focus on this today, geometric means go until you have a success. You're just going to keep doing it over and over and over again until you get what you wanted to have. Is there a limit to how many times you can do that? No, technically you can flip a coin forever and never get a heads. It's not really likely, but it's totally possible. So when we go through a geometric probability model, you need to stop, like if we're going to do a geometric problem, the information that you need to give me is the distribution, and that's noted by saying geometric, parenthesis, P equals. It's all you need to give me for a geometric model. You tell me what the X represents, what we're describing, give me context, but that's the work of the geometric model. Geometric is actually even easier to calculate everything just the regular way than it is to actually go through your calculator and get it to do everything for you. But if we're asking for the probability that the first success occurred some specific position, if the first success happened on the 5th time, that means I had 4 failures. All right, so fail, 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 yay! Success. So that's why it's Q for failure to the X minus 1, because on that last shot you did win. Expected value is very easy to calculate. It's just 1 over the probability of success. So how many times should I expect to flip a coin before I get a heads? 2. Probably say, within 2 coin flips, yeah, there's probably going to be a heads there. Standard deviation we're not going to use quite so much with this guy. But the standard deviation is root Q over P squared. So failures over the successes squared. Everybody should have that. We're good from last class? I don't recall. Did we get to do any problems with that? No. Okay, good. So we're just going to work problems. It's okay. Now again, just because they say the word chips doesn't mean we're talking potato chips. I have to remind myself that every single time. I don't know. Whatever. So here we've got a problem talking about computer chips, and it says that we're going to reject 2% of the chips produced because they fail pre-sale testing. Now before I answer any probability questions on this, I need to talk about what the model is, what everything is dealing with, because you've got to define it and show what work you need to show. So, write down what you think is probably going to be important for that. Shouldn't be that much. What should you be writing down? The reject is 2%. And that is not 0.2, that's 0.02. Saying that because I just wrote down 0.2. All right. So, what I'm talking about here is the probability of rejecting. I wanted to start figuring out what kind of a model this is. So first off, in order to use my geometric model, what do I need to have? Binary. My first thing I need is the binary. And that's going to be, I'm going to let the success, my P, be 0.02. And that means we reject. What would the other one be? What's the opposite of reject? Don't reject. I failed to reject you. And what's the probability that I don't reject? 0.98. And it's very important that you kind of start and talk about what the P and the Q are, because it gets really confusing when you're talking about the fact that the condition I'm looking for is to reject. To reject is a success in this case. So it's important to kind of write these guys out. So we have binary. What else do we need? Independence. What do you think? It didn't say. So if they don't say, we what? Hope it's representative. Okay. And then after independence, what was the other thing we had to have? Trials. And if it's a go until, which is what we're doing here, right? I'm going to define my X to be number of trials until first reject. It's important that you define that because we're going to have two different settings. We're going to have go until, and we're going to say, all right, I don't care no matter what, everybody's doing it 10 times, you just get to count how many went bad. Okay, so X is going to be the number of trials until the first reject. And then probability of success, is that constant? Always what? 0.02. So I can use your geometric model, and what I'll say is I will say geometric, where P is 0.02. So far, so good? Assumptions and conditions, talking about the model that you've got, defining your variable. Yes, sir?
For the go until trials assumption, is it always going to be that go until finite?
For geometric, yes. In order to use geometric, you have to have go until. Okay, and so I'm defining X as a number of trials until your first reject, which is my success here. Now the first problem said the probability that the fifth chip is the first bad one. Okay, now the way that we write this, okay, is we would say the probability. Are we doing a go until problem? So I'm going to use X. Is it one specific number or a range of numbers? One specific number. So I'm going to write equals, and that number is 5. So you can either do the formula that says failures to what power? 4, X minus 1. Success. You can do it that way. Or you can say geometric, because of that equal to sign right there. Because that's an equal to sign, PDF or CDF? Did we even talk about that? We didn't talk about that. That's going to be PDF. So you have two choices. You have PDF and CDF. P df is discrete, which means there's just one value that we're looking for. Okay? So it's going to be geometric PDF, and look at this. To get there, you're going to go to your second vars. It's all the way at the bottom. And all we're going to type in is basically what it prompts me to put in. So the first thing it asks me for is the P. So it's 0.02. And that's what I'm going to put down here. I'm going to say, okay, P equals 0.02. And X, I know, I'm going to make it better. X equals 5. Those are the things that go into your calculator. So P equals 0.02, X is 5, boom, 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 there we go. Which is also the same thing as if I were to do 0.98 to the 4th times 0.02, I hope. Yes, it worked out the same. Okay, so that means my answer here is 0.0184. So that's the probability that she doesn't have a bad chip until she hits the 5th one. Yes, sir?
So it's geometric PDF when X is a single number.
CDF, it's a whole range of numbers. Good. So, which leads me to what question B was asking. B said, what's the probability you find a bad one within the first 10 you examine? Yes, ma'am?
So anytime it asks something like that, we have to show how that we're in.
What you do, and that's a really good question. So, like, they'll give you the setup for number 10. That stuff, like right here, is what you do. Then you start reading through the problem, and it says, okay, if it's a go until, I'm going to let X be that, define a go until, because there's going to be another one. We'll just use a different letter for that. We'll use Y. And then the thing that you need to show me is this piece right here, and either this or this. This is the one case in the whole year where calc speak is okay. All right? As long as you can give me that. And then give me that and give me the answer, you're okay. This is the only place in the whole year where calc speak is reasonable. Now, the last one says, or part B said, what is the probability that you find a bad one within the first 10? Ugh. Okay. So, what does that mean? What are the different ways that this, if I'm going until I have a bad one? When is it okay? What would work with this? Finding a bad one on the, would finding a bad one on the first one work? Is that within the first 10?
Yes.
Finding a bad one on the second one, would that work?
Yes.
Third? Fourth? Fifth, sixth, seventh, eighth, ninth, 10th? If I find a bad one on the 10th one, is that within the first 10?
False. No. Yes.
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 Okay, if you take Algebra 2 within 4 years of high school, and you happen to take it your senior year, did you take it within your 4 years of high school?
Yes.
Yes. So what we're looking at here is the probability that the first bad one occurs somewhere within the first 10. That means the probability that it happens on the first one, probability it happens on the second one, all the way up to the probability it happens on the 10th one. Nobody wants to do that much work, right? You don't want to calculate this other stuff 10 separate times. So what we do, because we're still doing geometric, so I'm still going to use geometric, and it's still going to be P equals and X equals, but because this has a range, this is going to be CDF. P is still 0.02. X is the 10. So I just go to my calculator, and I go second vars. I love it how it just messes with the lighting here. Geometric CDF, 0.02, 10. Go for it. Not a 0. 1829. There we go. So I want you to see here that calc speak is okay here. You need to have this little statement, and this you need to have the X defined. PDF is if that's an equal sign. CDF if it's going to be a range. And it's going to be like that thing right here, and especially the CDF, that's going to be the hardest thing for you guys to kind of get. All right? Okay. Other way you could have done it was to physically, oh dear Lord, write out and calculate out all of those. Nope! Even the AP graders are like, I don't want to look for that. I much prefer the geometric model on the calculator. Yes, ma'am? It was bad, wasn't it? It was like, oh dear, no. No, I don't like this. This stinks. So, would you say that the method on the calculator is better? Yeah. The equation is great for 1, maybe 2. But past that, you got to be kidding me. No! Yes. And again, I'm perfectly fine if you leave that out. I'm perfectly fine if you leave this out. The calculator speak here is okay, but I do need to have this probability statement because X indicates that we're doing a go until. That's not the only type that we have. Okay? All right. So, still using the same idea. We're not going to like relist out my assumptions and conditions. Using those other formulas that I gave you. How many do you expect to test before finding a bad one? What do you think? Where'd you get 50 from? You had to be smart and change it into a fraction, didn't you? 1 over 50. Yes, he is absolutely correct. And that's because we're doing 1 over p. That goes back to the formula for expected value. And the work I would expect here is just that. 1 over p. But you need to make sure you tell me chips. Because what do I always say? Context. 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 Slightly important. Context is the difference between a 4 and a 5 for the overall score, a 3 and a 4 for the individual scores. You got to be careful. Okay? So, we're going to kind of switch gears here. Talk about a different situation. See if you can work that one out. Okay. So I haven't gone through the whole thing yet. I was just writing down kind of like the background stuff. And what you need to understand, I'm typically not going to give you one of those problems with just one little question. Be one of those problems and you have to do a whole bunch of different things with it. So it makes sense to just check your stuff first. So binary, either you contacted them or not. And actually, I'm going to modify that. I'm going to say either contact and get the $100 or more or not, because this is going to be my success. They didn't say it was independent, so we're going to hope it's representative. Probability of success is the probability that we contact and we get $100 or more. So it's the probability that you contact times the probability that you get $100 given you were able to contact. So that was the 0.2 times 0.05. So my probability of success will be 0.01. So I'm going to go until I get my first 100 or plus donation. And that's going to follow geometric, where P is equal 0.01. Now this question was asking you, on average, how many people should she expect to contact before she gets a 100 or plus donation? What am I looking for? Over $100, but what am I asking you to calculate? I'm looking for the expected value of X. So how am I going to do that? 1 over P, so 1 over 0.01. What's that going to be? 100. 100 people. You are expected to contact 100 people until you get 100 plus donations. Does that make sense? Because we could say contact, but it's not just the people who answer the phones, it's everybody that I have to dial. And it's not just the people who answer the phone that I'm worried about, it's those who actually paid $100 or more.
Why is it 0.01 and not 0.05?
Because when we look up here, we're looking for my probability of success is contact and get that $100. So it's the probability of contact, 0.2, times the probability of getting the $100 knowing that you were able to contact them. Okay? You guys look like you're having so much fun!
Wait, can you go back?
Mm-hmm.
It says number of trials until the first 100 plus donation.
Yeah.
100 people.
No, did you read the problem? Problem said, on average, how many potential donors will she have to contact until she gets her first $100 donation? And this just so happens that in the problem they're saying 5% will give $100 or more. So that's why I put the plus on it. Okay? All right. So I'm going to shorten the work I want you guys to do with this. I want you just to go ahead and solve the problems. Don't worry about checking the conditions. But no, for a test or quiz, you'd have to do that. Okay, see if you can answer this. I will check the assumptions and conditions so you can see it. But just see if you can work out these problems. Okay, did you get A? A should have been straightforward. What is A? 12.5 people. Okay? Or men. Yes, you're right, because we're not looking at anybody. And they're doing that because colorblind tends to be more a male trait than anything else. Thank you. Okay? The problem with B is they're saying not within the first 4. There are a lot of different ways that you can do this. You can say the probability that it does occur starting with the 5th person or beyond. The problem is my calculator only works the other way, so I would do 1 minus the probability that it does happen within the first 4. I can do it that way. I can look at the probability that it is no for the first 4, which would be if the probability of colorblind is 0.08, what's the probability of not being colorblind? 0.92. And there are 4 of those, because you're saying nope, nope, nope. All sorts of different ways that you can do this. All we care about is that it does not happen within the first 4. So if I do it this way, it would be 1 minus geometric P or CDF? C, because you see that inequality. And you would simply say P equals 0.02, X equals 4. I don't know. Calculate that. Tell me what you get. I don't care which method you want to use. You agree with her on that one? 0.716? Because I don't know. I'm just asking. Which way did you do it? The geometric or the 0.98, 0.92, 0.92, 0.92? 0.92? And these all are interchangeable.
If I put down 0.92 to the 4.
Perfectly fine. I actually was going to do that, but I said if I did that, someone's going to wonder where that came from. So that is exactly the same thing as 0.92 to the 4th. Okay? Okay. All right, same setup. Changing the questions. Try these guys. Someone's got the hiccups. Hee hee hee. Noelle, is that you? Do you have the hiccups?
No.
Who is that? Hannah? I just like teasing people. It's cute. And I didn't freeze this. I was just working through it. Okay, so. Okay, so did you get the first one? Okay, and the work that I show here, I think I'm just going to start doing it this way from here on out because I like the way this is working, is just this. Okay? For the next one, why did I choose 9? Because it says before the 10th man. 10 is not before 10. So that's why I'm talking about 9. And what does it end up giving you?
1 minus 1.
Yes, because I'm talking about the other problem. Thank you. I appreciate that. Goodness. Thank you. Lord Augsburger. Come on. They get set on a problem. Yes, sir.
So for the probability of X,
Which problem are you looking at?
I guess it's this one. Yeah, on this one.
Which one, C or D? D, okay.
So you like can you not do that X is less than 10?
I don't want you doing less than 10 because whenever you do this, this number here is supposed to match with that number there. And if you put 10 here, it won't work if you put 10 here. Okay, does that make sense?
Does it always have to be less than or equal to?
Yes, because that's how.
I mean, I know it has to be less than.
Right, but for CDF, yes, because CDF means going up to and including. Okay, so that's why I understand if you had put the less than 10, it would have technically been the same thing, but then you would have had to know that this number here would have had to have been 9. Okay? All right, good job. Okay, so now you should be at the point where you could actually go through and do these problems. Okay, so I'm not going to go over the answers to these. They are going to be, and they already are posted. Oops, hang on a second. I just closed out.
Oh, it's okay. I can highlight you.
Okay. Well, it also should be in your handouts.
Oh, yeah.
Okay. So what we're going to do now is we're just going to keep moving forward. I know, just contain your excitement, guys.
Woo! Rats. We already did it.
I know, I'm going through.
Get it?
All right. So this unit is about probability models. We started talking about what it meant to be Bernoulli, success failure, independent trials, and the probability of success stayed the same. We talked about the geometric model, but that's not it. There is more to this. There's one more model. The geometric model was very specific that it goes until you have a success. But sometimes you don't have time to do that. I'm not going to sit here and keep going until I win the lottery. That's kind of silly. Most of us will be playing forever. So we need to say, all right, okay, well, why don't we do it this way? No matter what, I'm going to play 20 times. And I want to know what I should expect to win. I want to know how many times should I win. And guys, when you're gambling, please do not go until. That is what causes gambling addiction. Oh, I'm due for a win. I've lost 100 times in a row. The next time I've got to win. No, it doesn't work that way. That is a losing strategy. So the other model that we're going to be talking about is called the binomial model. Okay, which is kind of fun because we are actually doing the binomial model in functions trig right now. Yay. Now the binomial model says, you know what, I'm not just going to sit here and go until. The binomial model says no matter what, I'm going to have a set number of trials. That's fixed. I don't care what happens, I'm going to do it 10 times. And then it asks for, within that set number of trials, within that 10 times, what's the probability I win twice? What's the probability I win 5 times? Okay? And therefore, when we're talking about the binomial model, remember before we had geometric? In geometric, we just said P equals, because we were going until a success. Now we're saying, okay, I have a set number. What is that number? N, and then what is P? The work that goes into this is going to be very, very similar. Okay? The assumptions and conditions that go into it is very, very similar. We used bits to remember geometric. Bins to remember binomial. The only difference here is, gee, what's B going to stand for? Binary. Success or failure. Bernoulli. Bernoulli is okay too. Binary. What is I? Independence. One trial must not affect the outcome of another. What do you think N means? The number of trials. That is your fixed number that you know before you even get going. Fixed. Biffs. Bits and biffs. Oh yes, Biff. The bad guy. And what was S? Success. Yeah, probability that success stays the same. I'm not changing my probability of success. That's it. Lemon squeezy. Okay? So the big difference here, and the way I like to think about it is geometric, go until. You have the G and the O, go until. Binomial, N is set. It's the only one that's got an N in it. Yes, ma'am? Bernoulli is the name of any trial that fits into that success or failure with independent trials.
Wait, so we had the geometric model and the binomial model. Wasn't there another model? Or?
We talked about Bernoulli, and again, Bernoulli is that idea that we fit those conditions in order to go forward.
But there's not a model.
Well, we did normal model, we did student's T model, we did chi-squared. All of those are models. Yay! Okay? So with the binomial model comes a few additional formulas. Nothing too crazy. No, it just flipped over. Thank you for noticing that, though. So please don't write this down. Do you remember this guy?
It's like one.
Yeah, the factorials is where, like, if it said 5 factorial, that's not meaning 5. 5, 4, 3, 2, 1. So this here, what you have to understand why this affects the binomial model. Let's say we're going to do 10 trials. And I wanted to know, what's the probability that I get exactly 3 successes? Well, that could happen on the first 3, the last 3, the middle 3, 1, 3, and 9, 2, 4, and 8. There are so many different ways that that could occur. And this is a combinatoric. Combinatorics is basically an arrangement of objects. Combinations is where order doesn't count. Permutations, order does count. So all this is saying is out of n objects, choose 3 of them to work. And that's the calculation that we use to get there. And n factorial is just saying, for example, 5 factorial, 5 times 4 times 3 times 2 times 1. Please do not freak out. We're going to have our calculator do all of this with us. And the important thing here is that it's like that whole idea of, we did it before where we said, okay, there are 6 cans of soda. And you're going to pop the top on them, and it's either a winner or not. Or back in the day, they used to do that with Snapple. You like pop the top off, you could read under the lid, you either won or you didn't. You don't care if it happened on the first bottle in the container or the second bottle in the container. You care that you get so many wins. Okay? So we have to understand that and remember when we were doing that last unit where we were talking about, okay, what's the probability that you get one person who says likely and one person who says unlikely? We said, well, that could be yes and then no, but it could also be no and then yes. This takes care of that, where order is not important. All right, so the formulas that we really pick up that you do need to write down. N is your fixed number. N is the number of trials that you're going to do no matter what. I'm going to go to the casino. I'm going to play slots with the $20 that I have in my pocket, and once that's gone, I'm done. Hopefully I come out with more money than I went in, but I'm not going to keep pushing my luck. P is that probability of success still. That's not changing. Yes, quickly. Which means Q is the probability of failure, or you can write it as 1 minus P. Nobody cares. It's all good. And the X, in this case, is the number of successes in N trials. And what I'm going to do is I'm actually going to be referring to this guy as Y. So I'm going to let X be the go until. And I'm going to let my y be number of successes. Okay, that's why you want to define that. Our formulas end up being the probability of having exactly x successes is out of n objects, choose x of them to be successful. For the probability of success, you have x of those. And failures, you have the rest, so n minus x. And this is going to be one of those cases where you will probably never actually calculate that by hand. You are going to use your calculator to do this, so please don't freak out about that. The expected value, the mean, is simply n times p. Oh, okay, there's a 20% chance of success. I'm going to play the game 10 times. Just would kind of make sense that I should win about 2 times. In the long run, my average. And the standard deviation is root NPQ. Okay? We good? Got that down? Because you will be dealing with standard deviation of this guy. So let's just do some problems. We are full of problems today. So, write down what you think may be important here. This is just like the geometric. You should start by doing what? Your assumptions and conditions. So what are my conditions I need to check? Before that, binary. Is this binary? Yeah, because you either hit the bullseye or you don't. The next one then was independence. What do you think? It says yes. It doesn't. Don't even need to hope representative. It says it's independent. And what's the last thing? Probability of success. So what are we denoting our success? Success is what? What am I considering a bullseye? Bullseye is my success. So this is where I am so far. Okay, now I'm going to take a peek back at those questions. I want you to read both of them. Geometric, binary, both. What's going on here? Or binomial? Binomial, both? There's a keyword in A. First. What does first mean? But what kind of distribution is that? That's geometric. So, what I need to understand here is X is going to be number of trials until the first bullseye. And that's going to be geometric, where P is equal to 0.8. The other one, I'm just going to call it Y, is going to be what? Is that geometric? Is that binomial? She misses the bullseye at least once. Is that a go until problem? No. So what that is that's the number of successes.
What do you say y is? The second question.
Yeah.
Oh.
So y is the number of bullseyes out of, and we said 6. So that guy is going to be your binomial. And that one, n is 6, and p is still 0.8. That's why I like to define the variables right up at front, because these problems do bounce back and forth. You all right? Hanging in there? I know, it's the most exciting day of the year. Not. All right, so A is asking you to find what? Probability.
First bullseye. On the third arrow.
First is on the third. So if I'm talking about the first occurring on the third, am I dealing with X or Y? X. Because we're talking about first. So that means I'm looking at the probability that the first success occurs on the third shot. Is that going to be PDF or CDF? PDF. And I'm just going to say P is 0.8. X is, what's my number for X here? 3. So go ahead and calculate that. Okay, what do you get? .032. Okay, good. See if we agreed. You see, even that's what they're doing here. 0.032. And I don't care if you wrote out the formula. Now, for part B, it's asking you what? Misses at least once. So when I'm talking about that, is that X or is that Y? That's Y. At least. What kind of a math symbol is at least? Less than or equal to? Greater than or equal to? So if I say at least 6 people, does six people qualify? Yes. So this is greater than or equal to. The problem is my geometric stuff, my binomial stuff, yeah?
I'm confused why it's greater than or equal to.
Because I was, wait, hang on, there should be ones. Why it's greater than or equal to? If
Oh, no, now I get it.
Okay, yeah, sorry about that. I was talking about,
I thought it said only 6.
I know, I was using 6 because, as an example, and then I didn't switch back in my brain. All right. So the problem here is that your calculator is only going to work on the left side, on the less than side. So you're going to have to do 1 minus the probability,
Why does our calculator only work on the less than side?
because that's just the way it's set up. It's kind of like doing the normal CDF. It only calculates, it automatically puts in and says, okay, whatever number you give me, that's my upper bound. The lower bound is negative infinity. Okay? So we're going to do 1 minus the probability that y, what's the opposite of being greater than or equal to 0? Less to 1. Less than 1? How many numbers are less than 1? Nope. How many trials? How many total arrows could I hit a bullseye? What's the fewest number of bullseyes I could hit? 0. I know. I got to put it in context. Context. And so I'm going to do 1 minus, is this binomial or geometric? Binomial, PDF or CDF? PDF, because of that equal sign. I'm going to say n is 6, p is still that 0.8, and x is 0. Okay. What do you get? Give you a hint. It starts with 0 point. Boom, boom. Nobody wants to risk it?
It's like times 10 to the negative.
No. Oh, I'm a dork. You want to know where I screwed up? Do you understand what I'm talking about here? My probability here is probability of hitting the bullseye. I don't want that. I want the probability of missing. Yeah, you're still going to do 1 minus that. It's just going to be a 0.7379. Sounds happy to me.
You have to do 1 minus.
Yeah.
Oh, 1 minus.
Good catch, Anna. Okay? All right, we're going to stop here, and we're going to pick up with this next class. I am going to just fast forward to the homework. So next class, what we're going to be doing, ladies and gentlemen, is we're going to be finishing these practice problems. We'll be doing some more practice problems over geometric and binomial. No additional new information for the rest of the year. Okay? So Friday, finish this up. Tuesday, quiz. Thursday, test.